Good morning and welcome to the postgraduate video course on advanced hydrology. We are into a stochastic hydrology module and we looked at various simple concepts of probability, etc., and how to fit probability distributions. That is what we were doing in the last class. We also looked at what is called the testing the goodness of fit. Once we have fitted a particular distribution, how do we know or how do we find out or how do we quantify whether the fitted distribution is good or bad? We looked at a test called chi-square test in the last class. We looked at the procedure, step-by-step procedure of how we can carry out this chi-square test. Then we looked at one numerical example of carrying out this or implementing the chi-square test. We looked at the example of the exponential distribution in which the random variable was the inter-arrival times, for which 10 different data points were given. We found the average, the parameter lambda, which is 1 over x bar, and then we carried out the various steps which are required to determine whether the fit is good or not. And then in the final analysis we had found out that since the computed chi-square statistic was less than the standard one, that is why the fit was good at 5% significance level. So similarly, we can test this goodness of fit of more than one probability distribution fit to the same data, and then we should be able to say that this particular distribution is better than the other one, and so on. Okay. So with that, actually we complete chapter 11 from the Venti Chow's book, and what we will do today is we will start chapter 12 on frequency analysis. So here we go. We have chapter 12 within this stochastic hydrology. It is on. So we are looking into this chapter 12, which is frequency analysis. Okay, so what is frequency analysis and what do we do in this is, basically the objective of a frequency analysis is to determine a relationship between the magnitude of a particular event or a variable, that is random variable, and its frequency of occurrence. So this is the main objective, in which we want to be able to say that this magnitude will occur with a frequency of so and so. All right. So using the data, historical data about that particular hydrologic random variable, we would be able to establish a relationship between the magnitude and the frequency of occurrence. All right. And there are many methods available for that, and that is what we are going to study in this particular chapter. Okay. So if I want to define it here, what we will do is, the objective of frequency analysis of the hydrologic data is, as I said, to relate or to establish a relationship between the magnitude of extreme events. Normally we are more interested in floods and droughts and other extreme events, to their frequency of occurrence. How? Well, through the use of probability distributions. Okay. So what we are saying here is that we will establish the relationship, or we will relate the magnitude of an extreme event such as a flood with its frequency of occurrence. All right. How we will do it? We will use certain probability distributions. Okay, a particular type of hydrologic variable will follow a particular probability distribution. So we will fit that distribution, and using that distribution we will establish that relationship. Okay, so we will look at some of those things. Now, looking at some basic concepts about this frequency of occurrence. For example, if I say that your Q is at a particular location in a river is 100 meter cube per second or 1000 meter cube per second or 10,000 meter cube per second. Which of these events do you think will be occurring with a higher frequency, or and which one will be occurring with a less frequency? Okay. By intuition you can say that the lower is the magnitude. So, out of these, let us say 100 meter cube per second will occur more frequently, right, will occur maybe more than once in a year, all right, or it will occur a lot more frequently than the other event, which is Q is equal to 10,000 meter cube per second, all right. So, higher the magnitude of any event, all right, lesser will be its frequency, or it will be more rare, or it will occur very rarely, all right. So, from intuition we know that, but we need to quantify that relationship, and we will do that using certain probability distributions. So, before I go to that, let me say that higher the magnitude lesser would be its frequency of occurrence. And vice versa. Okay, the opposite is also true. If the magnitude is less, all right, it will be occurring more frequently. Okay, now moving on, before we actually look at the various methods that are available for carrying out this frequency analysis, let us look at some of the assumptions which are made while carrying out this analysis. Okay. What is assumed is that all the events which we are using, or the data, are independent of each other. What do we mean by that? When we say that the events are independent of each other, let us say we are looking at the annual peak flow series. You have 50 years of data, all right. So, what was the value of the annual peak discharge, let us say 1970, has no bearing on what will be the annual peak discharge in 1990, or what was the annual peak discharge in 2001 has no relationship with that which is going to occur in 2002, all right. So, that is what we mean when we say the events are independent of each other. There should not be any correlation. So, that is the basic assumption. The next one we say is that the events are identically distributed. Okay. Again, what do we mean by this when we say that the events are identically distributed? Means, let us say if you have 50 years of data or 50 data points, all of those data or all of those observations follow the same distribution, all right. The characteristics in the catchment or the manner or the pattern in which these random events are generated are governed by the same probability distribution, all right. So, there should not be any major changes in the characteristics of the catchment such that we can assume that the data come from the same population and that population follows a particular probability distribution. So, these are the assumptions basically so that we can apply the principles which we have. The next one is the hydrologic system which is producing the event is what? Is stochastic. So, it is not deterministic in nature, all right. So, we are saying that it is uncertain or stochastic, is space independent, and time independent. Okay. This one is a crucial assumption actually, because we know that this assumption will be violated more often than not. Okay. Because the hydrologic system, we know there is a deterministic, there is conceptual models also available, but because of the fact that the complexity is such that we are not able to understand that, so we can assume that it is stochastic. Also we are saying that these events are spatially uncorrelated and also uncorrelated with respect to time, which again we know that is not the case, all right. But we carry out the frequency analysis under these assumptions. Okay. So, let us move on. The next thing we are going to look at is why we need this, or what is the application of your frequency analysis. Any idea why it is needed? Well, I will just try to list some of them. First and foremost is the hydraulic design. Of your major hydraulic structures such as dams, bridges, culverts, and other flood control structures. Flood control structures such as levees, all right, channels, etc. So, what do we mean by this? When we say that the frequency analysis is useful in the hydraulic design, all right. You know that how do we design a hydraulic structures? For example, a dam or a bridge. Let us say you want to build a dam or you want to build a bridge across a river. Okay. So, the bridge actually is normally designed for some magnitude of the peak discharge which we want to it to pass through, all right, safely. The magnitude of that peak discharge for which we design that bridge, all right, which is going to be correlated with what? With its frequency of occurrence, all right. Let us say we are going to design it for a recurrence interval of 100 year, all right, or a return period of 100 year, all right. So, its frequency of occurrence is once in 100 years. But the data that are available to us is, let us say, only 50 years or 55 years. Okay. So, what we need is we need to carry out some kind of extrapolation, all right. So, we establish a relationship between the magnitude and the return period, and then we can extrapolate, find the magnitude for 100 year for which we can design the structure. Okay. Number 2 is to determine the economic value of the flood control projects. Okay. What do we mean by this one? To determine the economic value of a water resources project or a flood control project. Okay. When we carry out the flood frequency analysis, what we are able to get is the probability of exceedance, all right, of a particular magnitude flood or some particular magnitude event. Okay. Using that, we can determine or find out what is called the risk associated with a particular project, all right. We would like to be able to find out what is the probability that the design flood for which this particular project is designed will be equaled or exceeded during the lifetime of a particular project. Let us say you are building a bridge. The lifetime of a bridge is, let us say, 100 years. In that 100 years, what is the chance, what is the probability that this magnitude for which it is designed will be exceeded or will occur. Okay. So, that probability will actually determine the reliability of that particular water resources project. Okay. And that reliability and risk associated we can determine using the frequency analysis. All right. So, to determine the economic value the economic value of that particular water resources project will depend upon the risk associated with it. If the risk is less, all right, we may want to go ahead and build the project, all right, or we can take the water resources decision depending upon that risk associated, all right. So, this kind of stochastic information or statistical probability in terms of reliability is very useful in determining the economic value of a particular water resources project. Moving on, the third advantage or application of this frequency analysis is in the floodplain management. Floodplain management. Okay. What do we understand by what is called a floodplain management? Okay. we have two types of flood control management kind of things. One is the structural measures, other is the non-structural measures. So, when we are talking about the floodplain management, we have these two type of methods to protect the people and the property from the flood. For the structural measures, all right, again as I said, we need to design those things for which the frequency analysis is useful. For the non-structural measures, what we do is we study the floodplain or the extent to which the waters will spread out during a flooding event corresponding to a particular magnitude, all right. To demonstrate this, let me show you that. Let us say this is a river, okay, which passes through a city, all right, and towns, all right. So, this is a river flowing in this direction, okay. You have the cities and towns on either side of it, okay. Now, you want to delineate the magnitude of the flood hazard, or you want to develop what is called the flood hazard map, okay, along this river, so that the people who are living in the flood plains will be able to buy the insurance or will be able to take a decision depending upon the magnitude of the flood. Okay. So, let us say I am going to delineate different boundaries in hydrology, but in all the different fields, other branches of engineering and even sciences and so on, wherever the problem is such that this particular distribution can be applicable or can be useful, all right. So, what we will do is we will look at the binomial distribution first, its corollaries, okay, this in the pink color. So, you should not have any construction or any activity in this area, all right. Similarly, we can carry out further analysis and we can find out the magnitude of an event which is higher than this, right. Let us say the green represents a 50-year event, 15-year flood. A 50-year flood obviously will have a higher magnitude than the 25-year flood, right. So, if you delineate that, it will be bigger than this. So, let us say this is your 50-year flood, okay, which will be bigger than this on either side. I am drawing it very nice and easy, but you know that depending upon the topography and the slope and everything along the channel, you will have different types of boundaries, okay, which of course can be delineated, all right. Similarly, if you want to use or draw what is called the, let us say 100-year event, it may be higher than this, all right. So, this correspond, the blue lines correspond to what? The 100-year event or 100-year flood. So, you see that we can manage the flood by minimizing the damages which can be caused due to the different magnitude floods. How can we do that? Well, we need to know the magnitudes of those floods depending upon the frequency of occurrence, all right. in the United States, they have a national flood insurance program, according to which what they have done is they have mapped all the major rivers in the whole country. All right. So, you have these flood maps available for any ordinary citizen or for the businesses and so on. So, you can get these maps for free from the government and then buy out your own insurance. In the US, the responsibility of the damages due to flood is not on the government. It's your own responsibility of the citizens, all right. But in our country, in India, the responsibility is lies with the government, all right. So, there is a major difference in how we actually manage the floods, all right. So, flood management is a very important topic in which we need the help of this frequency analysis, okay. All right. So, let us move on. What we are going to do is, we will look at, before we move to the frequency analysis method, we will look at a very simple method of relating the magnitude and the probability. This method is what is called the plotting position method. I am sure you may have seen this in your earlier classes. Maybe it is called something else, the plotting position. What is it? It is nothing but the probability assigned to every observation in a data set or in data. How it is done? Well, there are many methods available of determining this probability. Okay. So, what we are saying is that we will carry out a very simple method which is called the plotting position method, in which what we do is we calculate or estimate what is called the plotting position. And what is a plotting position? It is nothing but the probability which is assigned to what? To each observation. For example, let us say you have 50 years of annual peak flood data. Okay. So, you have 50 values of the peak discharges. What we will do in the plotting position method? We will assign a probability of occurrence or the frequency of occurrence or the probability of exceedance actually to each observation or each magnitude of the annual peak flood. All right. How do we do that? Well, it is a very simple method. I am sure you have seen it in your earlier classes. We arrange the data in the descending order. All right. The highest magnitude flood or highest magnitude event we put on the top. We assign a order of 1 to that. Then the next highest is the second one, the order will be 2 and so on. So, we arrange all the observations in the descending order of magnitude, and then we use a particular equation to calculate the probability of exceedance or the plotting position, right. Okay, so, let us look at that. So, if we have n as the total number of observations with us in the data set, and m is what? M is the rank or order of what? Of a particular observation or data point in what? In a list of descending magnitudes. So, what we are doing is we are arranging all the observations in the descending order. We assign an order of 1 to the top value, 2, 3 and so on, okay, and that this column, let us say we call m, all right. So, m can assume any value from 1 to n, okay, n is the total number of data points, okay. And then x subscript m we say is the magnitude of event of order m. Okay. So, now what we are going to do is, let us say we have the data and different data points, observations, we arrange them. So, we determine what is m, alright. M is the order which will vary from 1 to n. Okay. So, there are many formulas available to calculate what is called the probability of exceedance, alright, or what is the plotting position. Okay. So, what I am going to do is, I will write down all of this, maybe discuss very briefly their merits and demerits. Okay. And one of them, which is the Weibull's formula, I am sure all of you may have seen in your earlier classes. Okay. So, let us start looking at what is called the plotting position formula, which basically gives you what? The probability of exceedance. Okay. What is this denoting? This is the probability of random variable x having a magnitude greater than or equal to what? Xm. Xm is the magnitude of that rank m. Okay. And this is called the probability of exceedance. And let us say we denote it as small p. Okay. Okay, so let us start looking at many of these formulae. California formula is the first one, in which we say that the p is, or the probability of exceedance is given by simply m over n. Okay. So, when value of your m is 1, the probability is 1 by n, let us say n is 100, for m is equal to 2, it is 2 by 100, 3 by 100 and so on, alright. So, what will be the probability of exceedance for m is equal to n? Well, it will be 100% for m is equal to n. Okay. But whenever we talk about the probabilities, alright, can we be 100% sure? Can you say that the flood magnitude next year will be equaled or exceeded, will be this much with 100% accuracy or with 100% confidence? No, alright. So, we need to modify this formula. So, what people have done is they have modified it. Being able to say everything, something about probability with 100% confidence is not possible, alright. So, what they say is that then p, later on this is modified as m minus 1 over n. Okay. However, this formula also has slight problem. Why? Because the value of will be the probability of exceedance will be 0 for what? For your m is equal to 1, alright. Well, then what do? Where we go to some other formula. So, different people have proposed different formulas. This is proposed by Hazen in 1930, according to which it is given by this is m minus 0.5 divided by n. Okay. Another formula is the Weibull's formula, which is the most commonly used. This is E and this is I. Weibull's formula, in which the probability of exceedance is given by what? That is right, it is m over n plus 1. I am sure you have seen this in your earlier classes. Then another one is Chagoryev's formula. It is a Russian scientist, according to which the probability of exceedance is given by this m minus 0.3 over n plus 0.4. Okay. Then there is one what is called the Bloom's formula, which is given by m minus 0.44 over n plus 0.12. And then there is Gringorton's formula, Gordon's formula, which says that this probability of accidents is given as m minus 3/8 over n plus 1/4. Okay. So, you see that there is so many formulas available to determine this plotting position. All right. Now, the question that arises is which one am I going to use? All right. So, this depends actually upon the characteristic or the pattern that are involved in a particular data set or in a catchment. All right. So, different people tend to use a different formula, but the criteria is that any formula which you used should be unbiased, all right, and it should give an estimate which reduces the variance in our data. All right. So, the choice of method would depend upon two things. First one is the unbiasedness. All right, means what? You see that some of these equations will be biased towards either the higher magnitude flow or the lower magnitude flow or and so on. Okay. So, you need to be able to use something which is not biased towards any magnitude flow, and the other one is the minimum variance, okay, which minimizes the variance from the fitted line which you are going to have. All right. Okay. So, all of these formulas, then what we can do is we can write a general equation, general formula, all right, which is what? Your probability of x greater than equal to xm then can be described as m minus b, right, divided by n plus 1 minus 2b. So, this is a general plotting position equation, all right, and then b can be chosen as per your method. Okay. Or one can use actually 2-3 different methods and then determine which one gives you the best results. Okay. So, this is a what is called a very preliminary or a very approximate method of carrying out the frequency analysis. Okay. Now, what we will do is we will define or move into what is called the very general method, but before we do that, let us look at what is a return period. Because the frequency of occurrence or the probability exceedance which we have just seen can be represented by another term which is called the return period. I am sure all of you have seen this term before and know what it is. So, we will just define it quickly. What is a return period? It is a return period of an event of a given magnitude right may be defined as the average recurrence interval between two events equaling or exceeding a specified magnitude. Okay. So, what is a return period basically is that it is again the inter-arrival time on an average over a very large period between two events. So, on an average, all right, what is the time interval elapsed or the recurrence interval between two events which are of a magnitude which will be equaled or exceeded once in every, let us say, t years, and this t is what is called the return period. All right. Now, this t is given as the reciprocal of the probability of exceedance, x greater than equal to xm, or this is 1 over p. So, you see that we just looked at what is the plotting position method in which we determine the p or the probability of exceedance. So, if we have the data, quickly what we can do is we can just arrange them in the descending order. We can find out the probability of exceedance, we take the reciprocal of that, and then that will give us what? The return period. Alright. So, quickly in an Excel sheet you can do that actually. So, you have the magnitude of the flood or magnitude of an event, it may be rainfall, it may be wind velocity, any hydrologic variable. So, you have the magnitude, and associated with each magnitude you have what? The return period. Alright. So, you have established a relationship between the magnitude and the frequency of occurrence. Alright. So, you can plot that, and then that will give you the equation, and then you can fit a line or an equation to those data points, so that you will be able to get what is called the frequency analysis or the fitted equation, so that you can do interpolation, extrapolation, or do some kind of stochastic analysis. Okay, so moving on, what we do is, once the probability or once the plotting position is determined, it can be plotted on a probability paper. Okay, where your x axis represents what? The plotting position or the probability. Okay, or the return period. It can be in terms of the return period, and y axis is what? Y axis actually represents your magnitude of the event. Okay. Okay, now we will move on and look at something very interesting and something very important. Okay. We have seen the plotting position method, and actually before we move on to the other methods of frequency analysis, we will look at a discrete probability distribution called the binomial distribution, right. And this binomial distribution is very important not only in hydrology, but in all the different fields, other branches of engineering and even sciences and so on, wherever the problem is such that this particular distribution can be applicable or can be useful. All right. So, what we will do is we will look at the binomial distribution first, its corollaries, some results which can be deduced, and then I would like to look at an example based upon the binomial distribution. Okay. So, let us first look at binomial distribution. As I said that binomial distribution is a very special type of distribution which is applicable under very unique or different kind of situations. Okay. So, let me define those things, when it is applicable and what are the criteria under which we can use this. First one of them is that any event has only two possible outcomes. Okay. What do we mean by that? Well, we can apply the binomial distribution to a situation in which you define an event or you have an event of which there can be only two possibilities of outcome. Okay. And the classic example of that is tossing the coin. When you toss a coin, you will either get a head or tail. There is no other possibility. All right. Similarly, how can we apply this kind of concept in hydrology? Well, you can define that the magnitude, a particular magnitude of peak discharge in a river constitutes flood. For example, let us say you have river Ganga, in which the in a particular region, let us say close to Varanasi or somewhere, the flood will occur when the magnitude of the discharge of the a river exceeds, let us say 100,000 meter cube per second. So, once you have defined that, you would be able to say that the next year whether it will flood or the area around that particular river location, whether it will flood or not flood. There will be only two possible outcomes. All right. So, depending upon the magnitude of the particular event, the outcomes will only be two. So, we can actually define our event in that manner. All right. So, this is one particular characteristic of your binomial distribution when it has to be applied. Other one is that the probability of these two events, okay, either this or that, are known beforehand, and this is called what? Occurrence. Probability of occurrence is, let us say, defined as P, and the non-occurrence is defined as what? Let us say Q, and Q will be equal to what? Based on our law of total probability, it will be 1 minus P. Okay. So, you see that when you are tossing a coin, you will have a head. All right. The probability of head is, if it is 0.5, what is the probability of tail? It is 1 minus 0.5, which is also 0.5. All right. Or in case of hydrology, if the probability of occurrence of flood is, let us say, 20%, then non-occurrence will be 80%. All right. So, they are complementary to each other. Third one is that the two events are what? Are independent of each other. Okay. All right. Well, again, I think you know this concept when we say these two events are independent of each other. When do we say that? When the occurrence of one does not depend upon the occurrence of the other one. All right. When you toss a coin, let us say 10 different times. All right. So, does the probability of occurrence of head 9th time depends upon what happened during the 2nd time or 3rd time or 5th time? No. So, all these events are independent of each other. Similarly, in case of hydrology, we assume that the occurrence of flood during any given year is independent of what happened in the past. All right. If a flood occurred in 1971, it has no bearing on what is going to happen in 2000 or the next year and so on. Okay. Although there may be a little correlation, but we ignore that. Okay. So, these are some of the conditions. Okay. And then the last thing I would like to say about binomial distribution is that it gives a very specific type of probability to us. Okay. What does it give? We are saying that it gives us a very specific type of probability of occurrence. And what is that? We are going to look at in the definition of this binomial distribution. All right. So, let me say then, the binomial distribution gives us what? The probability of occurrence, of what kind of event? Of an event. Now, this is interesting and important to understand. R times in n successive years. Or trials. Okay. Is this clear? So what does the binomial distribution give us? It gives us the probability of occurrence of an event r times in n successive years or n successive trials. For example, let us say you flip a coin 20 times. So n is equal to 20. So you are carrying out 20 trials. Out of those 20 trials, you want to find out what is the probability that the head will occur exactly 5 times. That is r is equal to 5. So you are trying to find out a probability of getting a head 5 times out of 20 trials which are carried out independently and successively, one after the other. There should not be any gap. All right. Similarly, we can how is it useful in hydrology? Well, we may be interested in finding out in hydrology that what is the probability that a flood will occur 2 times in the lifespan of a dam. The lifespan of a dam may be, let us say, 75 years. So we may be interested in finding out what is the probability that the flood will be equaled and exceeded. The design flood for which the hydraulic structure has been designed will be equaled or exceeded exactly 2 times or exactly 5 times in the lifespan. Okay? And that probability will be very useful in finding out and in the design of the structure and in determining what is the risk and reliability associated with that particular structure. Okay? So this is the kind of probability it gives, and there is an expression or formula which we will write directly. I would not like to go into the mathematical proof or the details of that because this is an applied course. All right. So this probability is given by this. This is denoted as P r comma n. That is how I am going to write. Different books will follow different notations, but you understand what is P r comma n. It is basically giving you what? It is giving you the probability of occurrence of an event, what? R times in n successive trials, or in case of hydrology we can say R times in n successive years. All right. So this is equal to n c r p to the power r and q to the power n minus r. Okay. So this is the final actually result. I do not want to go into its derivation. Okay. So the probability of occurrence of an event r times in n successive years is given by this formula, where what is NCR? It is a combination. Okay. From your knowledge of permutations and combinations, your NCR I will give you is directly given as the n factorial divided by n minus r factorial divided by r factorial. Okay. So that your P r comma n is going to be equal to this thing, all right, times p to the power r and q to the power n minus r, where r is the number of times exactly the event will occur out of n different trials. Okay. Again, I will take a couple of corollaries of this, or results which can be deduced out of this. The probability of an event not occurring at all, can you find it, in n successive trials or years. Okay. Can you find it out from the binomial distribution? Not occurring at all means r is equal to what? R is equal to 0, right? So all you do is you put r is equal to 0 in this, that is occurring 0 times and not occurring n minus r or n times. All right. Okay. So this you can say is what? P 0 comma n, where r is equal to 0. Not occurring at all means occurring 0 times, right? So you put r is equal to 0, you will have the result. So if you did that, you will have n factorial divided by n minus 0 factorial times r is 0. So 0 factorial times what? P to the power 0 times q to the power n, right? N minus r is 0, n factorial will cancel out, 0 factorial is 1, anything raised to the power 0 is 1. So, what would this be? This is nothing but q to the power n. So, p 0 comma n is what? Is q to the power n. What is this saying? This equation is saying that if you have n trials, all right, in each of these n trials, the probability is, let us say, q. What is the joint probability? Joint probability is q times q times q times q n times. We have seen that earlier when we did the that method of maximum likelihood, right? It is a similar thing here. So, if you apply these laws of probabilities intuitively, you will get the same result. Okay. I will actually like to go back to this this equation, this one, which gives you the probability of occurrence of an event r times in n successive trials, right? What is p raised to the power r representing? It is actually representing the probability of occurrence of the event r times, exactly r times. So, p times p times p times p up to r times, that is what it is, the joint probability of occurrence. What is this? Q raised to the power n minus r is what? If you have 20 trials and out of those 20 trials, you have 5 times, let us say r is equal to 5, you have this event is occurring 5 times, means what? It is not occurring n minus r times, or 20 minus 5, which is 15 times, all right. So, the total probability then has to be p to the power r multiplied by what? Its non-occurrence, which is q to the power n minus r. Okay. So, this is the laws of actually your joint probability of occurrence we are trying to apply. Now, what is this NCR doing here? Why do we have this? If you think about it, this combination can occur in many different ways, all right. We are saying exactly 5 times, but those 5 times can be first 5 years, last 5 years, somewhere in between, or there can be many such combinations. How many such combinations would be there? Well, NCR. So, we can derive actually this binomial distribution using our basic law of or basic probability. Okay. So, this was the first corollary in which we found out, or we said that the probability of non-occurrence of an event in n trials is q to the power n. Okay. What is the second one? The second result is this, wherein we say that the probability of an event, occurring at least once in n successive years or trials is given by this probability of at least once. Okay. This is also very important. Okay. Will be given by what? It will be 1 minus of probability of what event? Of not occurring at all, which we have just seen. Okay. So, if you are carrying out n trials, then what you are saying is that the probability that a particular event will occur at least once, all right, at least once will be equal to what? 1 minus it will not occur at all, all right, which is equal to what? 1 minus q to the power n, or 1 minus p to the power n. Okay. So, this is your at least once. Okay. This formula actually can be derived using the law of the total probability. Okay. So, let us say you try an event 5 different times. Okay. So, let us say n value of n is equal to 5, all right. So, what are the possible combinations of what can happen, all right. An event can occur, let us say, during the first trial, and it will not occur in the remaining 4, all right. Similarly, if r is equal to 1, then it can occur in the second one and not in the first one and the remaining one, and so on. So, this way you can have that the probability that your x will be equal to either 0, that is it will not occur at all, plus it will